Hello everyone, and welcome to page 31 in the workbook. In this video, we'll be looking at some common vector spaces and trying to write down standard bases for those. Okay, so before we dive into this new idea here, let's just remind ourselves of a fact that we've already stumbled up on in this section, and that is that vector spaces have a lot of different bases. Okay, but some bases are easier to work with than others, and so we introduced this idea of a standard basis. That's a basis for a vector space that's particularly nice or easy to work with. Okay, so take, for example, the vector space Rn, the set of all n tuples. Okay, our claim is that the set that we're looking at here is a basis for that vector space. Okay, and the vectors that you see in that set are given special names. The first one is called E1. That notation represents the fact that there's a 1 in the first coordinate and zeros everywhere else. The second one is called E2. That's got a 1 in the second coordinate and a 0 everywhere else, and so on, down the line until we get to En. So basically what we're saying is that that set has two properties. It's linearly independent, and it spans Rn. We can build any vector in Rn as a linear combination of those vectors. Okay, so if that's really true, that that's a basis, what would the dimension of Rn be? Well, it would just be the number of vectors in this set, and we can see that that's n. Okay, so Rn has dimension n. All right, next vector space on our list is Pn of R. Recall that represents the set of polynomials of degree n or less. Okay, standard basis looks like this. 1x, x squared, all the way up to x to the n. That's a linearly independent set that spans Pn of R. How many items are in that set? Okay, well, x is really x to the first. So notice that x to the first through x to the n, that's n elements, but then there's one extra one for the constant term. So we actually have n plus 1 elements in that set. Okay, so the dimension of Pn of R is n plus 1. Okay, and then we continue down to the set of all 2x2 matrices. Turns out that this is a nice basis. The standard basis for the set of 2x2 matrices looks like this. And we can introduce a little bit of notation here. That first matrix we'll call capital E superscript 1, 1. The 1, 1 really tells us that there's a 1 in the first row in the first column and a 0 everywhere else. And then similarly, this matrix we could write down as E1, 2. That just means that in the first row in the second column we've got a 1, and we've got zeros everywhere else. Okay, it turns out that this is a linearly independent set that spans M2 by 2 of R, and we see that there are 4 matrices in that set, which means that the dimension of M2 by 2 of R is 4. Okay, and we can generalize that basic idea to any set of matrices. So what if we wanted to talk about the set of all m by n matrices? Well, we could form a nice basis for that just by going through each coordinate one at a time and putting a 1 there and a 0 everywhere else. So we would get E1, 1, E1, 2, and we'd keep going. This list could be long if m and n are big until we get to EMN. Okay, that matrix would have a 1 in the mth row and the nth column and zeros everywhere else. Okay, and then the question is, how many matrices are in that set? Okay, what do you think we would get if we counted those up? If you think about it a little bit, I think you can convince yourself that you're going to get m times n. It's really the number of entries that are in an m by n matrix. Okay, so the dimension of that vector space that we're talking about is mn. Okay, and then finally, what about the trivial vector space, the vector space that only contains the 0 vector? Well, we talked once before about how the fact that by definition, a basis for that vector space is the empty set, and there are no vectors in the empty set, which means that that's a 0-dimensional vector space. Okay, so there's our list, and comment that we're making here, we're sort of declaring, we're using the word standard basis, which means that we're assuming that these sets are bases. Really, we would have to prove that. Okay, convince ourselves that these sets that we're forming really are bases. We could do that for all of these. I don't want to do that because that would be kind of tedious, but let's do it for just one particular case, just to reassure ourselves here. What if we wanted to prove that the standard basis for R3 really is a basis? Okay, so that would be going up to this first line in our chart for the case where n equals 3. Okay, so if we wanted to do that, we'd maybe start out by observing, by definition, R3 is just the set of all 3 tuples. Okay, and then we notice, using the technique we've been using, that we can break that ABC up into 3 parts. Okay, like this. Okay, and by doing that, we notice that R3 is the span of the 3 vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. Notice that that set of 3 vectors is the same standard basis set that we have up here. That's kind of our reason for calling that the standard basis, that it's so nice. It just kind of naturally fell out of our definition of R3. Okay, so we have expressed R3 as the span of those 3 vectors. We know from our previous work that we can convince ourselves that those 3 vectors, here, here, and here, are linearly independent. Then we have a basis for this vector space. Okay, so how do we show that those 3 vectors are linearly independent? Well, we would look at a matrix. And do row reduction, but the thing is, we don't need to do any row reduction. That's already in echelon form. Okay, we've got our 3 pivot positions there, and so our comment would be, okay, so since the matrix below has pivots in every column, okay, the set beta, just consisting of those 3 vectors, 1, 0, 0, 0, 1, 0, and 0, 0, 1, is linearly independent and therefore a basis. Okay, and then just a comment. Notice that because there are 3 vectors in that basis, that also proves that the dimension of R3 is 3. All right. And so we've proved what we wanted to prove, and maybe just one more comment as to why we chose to call this basis the standard basis. Really, it comes down to the fact that this calculation was nice. Showing that those 3 vectors were linearly independent was easy because of the fact that the matrix was already in its echelon form. Okay, and that's kind of the general theme with standard bases. We want them to be nice, easy to do calculations with.